So it turns out that thin lenses are one application of refraction that we actually use on a daily basis. And there's different types of lenses, so we're going to talk about these different types of lenses. So as I mentioned, these thin lenses are used in a lot of different uses, have a lot of uses that we see every day. So eyeglasses, contact lenses, cameras, microphones, telescopes. So basically everybody's got a smartphone now and you've got a camera on your smartphone. It has a lens in it. And so all of these different optical instruments use these thin lenses, and they're all based on this idea of refraction. So we need to define what a thin lens is, and it basically consists of a piece of a glass or plastic, and that piece of glass or plastic is ground so that the two surfaces on either of the segments are spheres or planes. So in other words, you take this thin piece of glass and then you grind it, or it's ground down so that it has some sort of an arc associated with it. And we use the thin lens approximation, which assumes that the thickness of the lens is basically negligible, so that we can measure what are called the focal points relative to the center of the lens. So, we can have thicker lenses, which would be like thicker pieces of glass, but all of the pieces that we're talking about that we're going to talk about in this presentation are essentially extremely thin. So things like the thin, contact lenses are extremely thin. Even eyeglasses are relatively thin. The lenses that we'll talk about will have one focal point. They'll have two focal points and one focal length, and we'll see, and I'll define what those two terms are. And there's two different types of lenses that we can talk about: converging and diverging lenses. So we want to think about how light actually bends, and we could do this with the PhET simulation, but instead of pulling that PhET simulation up and drawing all these pictures, or making all of these PhET simulations, I sort of made the PhET simulations and then took those pictures from it. So we need to think about how light bends through different types of surfaces. So here we have a triangle. I have light coming in. It refracts or bends towards the normal, and then it bends away from the normal. So we get this bending of the light in this fashion. If the surface is a little bit more flat, and then it would still bend, it just won't bend quite as much. If it's a flat surface, it goes straight through. And then, of course, we can have the reverse, where the light comes in, and then it's basically the reverse of this picture right here, right? It bends up, and then this picture is essentially the reverse of the first picture. But in general, when the light encounters a surface, it's going to bend, and it's going to bend a certain way based on the angle of incidence and the angle of refraction, what that surface is made of, and what those normals are. So again, in this case, the light comes in, it bends towards the normal, and then it bends away from the normal, and you get this large bending of the light with this triangle type shape. So we could think about how the light bends if we were to put these shapes together. So if I had a triangle shape, just a square shape, and then another triangle shape, we could imagine how the light would bend through each one of these different pieces. And so if I take those pictures that I had earlier and I put them together in terms of how the light bends through each one, I see that I end up getting a situation where light coming in parallel to each one of these pieces ends up converging to a particular point. And that point where they converge is called the focal point. Now I could imagine taking that same picture that I had in the previous picture, and instead of having a triangle, I start to make it a curved shape instead of that triangle shape, and I get the same effect. So, I have the light, and it tends to bend in such a way, the way that this shape is, so that it bends, so that the angle of refraction over here becomes larger, and they all bend to a particular point. So when I have this curve in this material where the center of the material is wider than the edges of the material, and that's what's happening here, the center is wider, and then they've got this curve associated with it, the rays of light coming in parallel tend to all converge to a particular point called the focal point. On the other hand, if I flipped the picture so that instead of having triangles at the top, the wider part is on the edges, I get a different effect. And so what happens here is that when the rays of light come in, they do bend, and they bend again away from the normal, but instead of coming together because this is reversed, it bends away from the way that it was coming in parallel at the top. It goes straight through, and at the bottom it also bends away. So the rays of light over here are diverging. They're never going to come back together again because they're always spreading apart. But if I were to take and follow those rays of light that spread out and follow them back behind the lens, it would appear as if they were all coming from a particular point behind the lens over here. And so we call that the focal point. And this is a situation where those rays of light are diverging. So we could do the same thing. Instead of having blocks, we could have a solid piece that had this curve associated with it where it's wider at the top and more narrow in the center. And as the rays of light come in parallel, they spread out due to refraction. But if I followed all of those rays of light back from where they were diverging, they would all seem to be coming from a particular point behind the lens, and that's called the focal point. So I sort of alluded to this already. We have converging lenses and diverging lenses. Converging lenses are such that they are thicker at the center and they are thinner at the edges. If I have parallel lines coming in, they converge to a particular point, and that point is called the focal point. The length, the focal length, is the distance between the center of the lens to that focal point, right? So that's the focal length. All lenses have two focal points and one focal length. So if I took that same lens and I reversed the rays of light coming in, so instead of coming in from the right, if they came in from the left, they would all converge to a particular point over here, and that's the focal point as well. And so if I measure the distance from the center of the lens to that focal point, that focal length would be the same as the original focal length. So there's only one focal length associated with a lens, but there is a focal point on either side of the lens. Converging lenses can have different shapes. I could have bioconvex, I could have convex, concave, but even, and so this is like, this could be something similar to a contact lens, for example, or even eyeglasses. So one of the things that's important though for converging lenses is the lens is always thicker here in the center and thinner at the edges, or it's actually a little bit even more beyond that. It has to do with the curvatures, and we'll talk some more about that. And here's a plano convex. Here's a diverging lens. So with a diverging lens, it is thicker at the edges and thinner in the center. If I have light that shines parallel to the lens coming in, it spreads out after passing through the lens, or we say that it diverges. If I were to follow those rays of light that exit the lens and diverge, if I were to follow them back through the lens, so all of these lines, I follow them back here, they seem like they are originating from some point behind the lens, and that's called the focal point. Diverging lenses have negative focal lengths, focal lengths, I guess I should say, which is the distance from the center of the lens to the focal point, and it's negative to distinguish it from a converging lens because the focal point is behind the lens. And so I can do the same thing if I were to reverse this and the rays of light came in parallel from the right, they would diverge. But if I followed them back, there would be a point where all the light seems like it's originating from. So remember, if my eye was over here, my eye would only believe that the light was traveling in a straight line and see it as originating from this particular point. If I measure the distance from the center of the lens out to that point, that's my focal length. And the focal length is the same regardless of which way the light is coming in parallel to the lens. So I have many different types of diverging lenses: bioconvex, convex concave, plano concave, but in each of these cases the lens is thicker at the ends and thinner at the center.